Yeah, hello. This is the first video that I'm going to present in this fashion, and it is about vector fields, and it's about the exercises that you did this Monday, and I have chosen a few of the exercises, and that is exercise 2, 3, and 7a in order to illustrate the subjects of last Monday. I'll start by showing you some of the extra commands that you will need in order to do vector calculus, and I have chosen to show you the commands in Danish because many of the Maple demos use these Danish expressions, and I have here listed the initialization that you could use, and you know that the dot product in Danish is called the prikprodukter, and it's abbreviated prik, and you can use this in order to get the dot product. Also, the cross product is called krydsproduktet in Danish, and you can use this abbreviation for the cross product. Also, if you need the components of a vector, you can use this procedure here, and it will give you, say, the coordinates of a vector. And then you have the gradient, you have the divergence, and you have the curl of a vector. And in Danish, curl is called rotation, in short ROT, and we'll use that in our computations below. But let's start, or I have done so, with exercise 2. In exercise 2 you have given a vector field, and you can, from this vector field, when you try to make the flow field, you can compute the system matrix for this flow field. And I explain to you what this means. I have here written the system matrix, and you can see that if you, from this system matrix, generate the vector, you will get these coordinates of the vector. The first coordinate is z, and the second is y divided by 10, and the third is minus x. And then you can, in order to get an impression of what you should expect when you look at this system matrix, and you want to solve the flow equations corresponding to the system matrix, you can take the eigenvalues of your system matrix, and you get one real eigenvalue and two complex conjugate eigenvalues. And then you know that there will be an exponential component, and there will be some oscillatory components of your solution. But you shouldn't bother to do the detailed manual integration of your flow equation. You should rather use the more powerful d-solve when you solve these differential equations. But let me first explain to you what are the differential equations. You see here, the first equation is the derivative of the first component of your vector field is equal to the first component in your vector field. Or I should say the derivative of the first component in your parametric representation is equal to the first component in your vector field, and the derivative of your second component in your parametric representation of your flow curve is equal to the second, and so forth. So now you have the equations that you want to solve in order to get your flow field, and you readily use dsolve in order to do so. And here I use dsolve with the initial point 1, 1, 1 to give you the solution. And you see, having made the solution, I can extract my parametric representation by looking at the right-hand side of the solution. So this is the first component of the solution, the right-hand side, and this is the second and the fourth. And when I write this down, I get this parametric representation of the solution. Also, I can find the derivative or the tangent vector to my flow curve like this. But this is a specific flow curve that passes through this point here. Now, what I want to do now is that I'm going to show you how the vector field looks like. And you know that if you have a vector field, then to each point in space you have attached a vector, and I can depict this by using the field plot 3D routine, and also I can depict my solution to the flow field, that is the flow curve that passes through 1.1.1 by using space curve, and then I can displace the two. And you see here you have here the flow curve. See, it circles in the xz coordinates like this, and then it is expanding in the y direction like this, and so this is the flow curve, and the flow field is shown by these vectors here, and you can see that they will generate such a flow curve like this. So this is the result. Now, if instead we want to see how, say, a line segment develops as u increases, I can do this by parameterizing this line segment. This is question C and D of the exercise. You can see the line, if I parameterize it in the following way with the parameter v, you can see that v is running from 0 to 1, and so if v is 0, then the point is 1, 1, 1, and if v is 1, then you have 2, 2, 2. So this is the parametric representation of this line segment. Now you can then solve your equations, but now you use as initial condition the parametric representation of your line segment. So you have when initial or when u is 0, you have that this is your line segment, and you solve for this for the components of your parametric representation. And now you want to make it into to a function, so you use the unapply command with respect to your two parameters u and v, and then you get this parametric representation of the surface that results when this line segment follows the flow lines. And then again you can use the field plot in order to show the flow field, and then you can use the surf or the plot 3D in order to plot your surface. And here again you see that you have this initial line segment. See if I can show you. It's from 1, 1, 1 until 2, 2, 2, and then it develops in this fashion as u increases. So in this way you can actually get a better understanding of what a vector field is like. Now for exercise 3, we have this function here, and we are looking at a specific surface here, and that is this is the level surface corresponding to the value 0. So you equate this to 0, and then you can very quickly see that if you put this equal to 0, you put the fourth on the other side of the equality sign, and then you divide by 4, then you have the standard equation of an ellipsoid, and it has the semi-axis in the x direction of 2, of square root of 2 in the y direction, and of 2 in the z direction. Also, you can compute the gradient of this field. It will be 2x minus 2 and so forth. This you could actually, just by looking at it, see that it will be like this. Again, we can show the field plot, but also we can show a plot of the ellipsoid, and we do that by making a parametric representation of the surface of the elliptic surface, and you have that it passes through the point, or the center is the point 1, 1, 1. You can see that of this from this expression up here, and then you have the semi-axis in the 3 directions, 2, square root of 2, and 2, and apart from that it is spherical coordinates here, and so this will actually be a parametric representation of the surface. Now you can display the vector field and the surface, and you see here, if you look at it in xz coordinates, you have a perfect circle. That is, you have you have equal semi-axis equal to 2 in that direction. In the other direction, or in the say in the yz plane, you have the semi-axis 2 in the z direction and the square root of 2 in the y direction. Then again, you can compute the tangent vectors to the surface. This is done by differentiating the parametric representation with respect to u and with respect to v, and you get that. And you can easily show that these tangent vectors are perpendicular to the vector field itself. So you evaluate the vector field for the parametric values, and you have to get the different components and put them into the vector field, and then take the dot product with the tangent vectors, and you get 0 for both vectors. Now, you can also, and you can look at this in another way, you can actually make a normal vector to your surface, and this is done by making a cross product of the two tangent vectors, and if you do this, you get this result here. And if you compare this to your vector field, you can see that the two vectors are proportional. And the factor of proportionality is square root of 2 sine u divided by 2. So if you multiply your vector field with this value here, you get n. And this is simply a check on this. So multiply this by k and subtract n, and you get the 0 vector. So the vector field is normal to this surface here. Now finally, for 7a, I want to show you how to actually find an antiderivative to a vector field. You have here the vector field y, cosine yx, and so forth. And in order to find the antiderivative of this, we use the stairline method. The stairline method, as is shown here, is not given in the e-notes, but it's given in today's Maple demo, so look it up. You integrate along the x-axis from 0 to x, and then in the next step you integrate along the y-axis from 0 to y, and finally along the z-axis from 0 to z. So you have this parametrization of your line of integration, and then you simply get this expression, because you see along the x-axis the unit vector is equal to the direction, or you simply get the x component. Along the y-axis you get the y component of the vector field, and along the z-axis you get the third component of the vector field. So this is the expression for this line integral or curve integral. And then you simply put in your vector field to see if y is 0, then this component is 0. You integrate that from 0 to x, and when here you have z is equal to 0, x is equal to x, and y is equal to u, and you integrate that from 0 to y, and for this you only get y, you integrate this, and this is the result of your computation. And then you turn it into a function by using the unapply command, and you have this this capital F function of x, y, and z. Now, let's see if I compute the gradient of this f function, I get exactly the same result as I started from. So, v is identical to the gradient of f. And this means that all antiderivatives are to this vector field are f plus an arbitrary constant. So, and this is all I have to say today. I hope you can use this this video introduction. That's the first I have made in this fashion. So let's I'll continue with another one on Friday. Thank you.